Hi, my wonderful Calc 1 students. Last class we did related rates. Now, related rates is a very important topic and uh, somewhat complicated, so we did a few examples in class, but even though we only did maybe 3 or 4 examples in class, you guys need to do a lot more on your own. So do as many problems from the book as you can, get really good at it. And then there was this one problem in the PowerPoint, example 7, that we didn't get a chance to do. And I had a couple of students come and ask me if I could post the solutions to this example 7. So I just decided to record a little video, do a little video solution to this one. So let's go ahead and take a look at this. Let's see, example 7. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so I know that a picture was provided with this example, but in general, don't assume that there's always going to be a picture given to you. So what I'm going to do is, you can go take a look at the picture, but what I would do right now is don't look at the picture for a couple minutes, try to draw the picture on your own, and then you can go look at the picture and go, okay, good, I was thinking about it the same way that is given in the picture. Okay, so what I'm going to do is I'm going to draw a picture. Now actually, I'm going to draw 2 different pictures. The first picture I'm going to draw is going to be the general situation, and then I'll draw one picture for the instant that they're asking the question. Because remember, this is a related rate problem. Things are changing with time. So the first picture is going to be in general what things look like. And then the second part is going to be, well, the question is asking you, at what rate is the thing rotating at a certain instant? So then I'm going to draw the picture at that instant. Okay, so let's start from the beginning and let's try to draw the picture for this. Let's see, it says a man walks along a straight path at a speed of 4 feet per second. So let me start off by drawing a picture. We'll call this the general picture. So over here, general. And the guy is walking along a straight path. So here's a straight path. And the guy's walking along at a rate of 4 feet per second. So I'm going to draw a picture of a man walking to the right at a rate of 4 feet per second. When you draw the general picture, you don't want to put any numbers in the picture unless you know those numbers are always the same. This guy is walking to the right at a constant speed, 4 feet per second, so that's okay. Now let's go ahead and take a look at the next part of the problem. Next part says, a searchlight is located on the ground 20 feet from the path. So we have a searchlight that's on the ground, it's 20 feet from the path, and it's kept focused on the man. But 20 feet from the path, here's the path the guy's walking on, and we have a searchlight 20 feet from the path. So for now, let me put a dot right here. Let's say that's the searchlight. And it's focused on the man, but it's 20 feet from the path. Now I want to stop for a second and make sure you understand this. In Calc 3 especially, you'll definitely need to understand this idea here. So what do I mean when I say this point is 20 feet from the path? The path is a line, this is a point. What does it mean to say the distance between a point and a line? What it means is the shortest distance. In other words, if I say what's the distance from this point and this line, you don't take a tape measure out and measure the distance from here to here. That's the distance from the point to the line, but that's not the shortest distance. So the 20 feet is the distance from here to here. This would be the shortest distance. Another way to say it is it's a perpendicular distance. So if that's the searchlight, you go perpendicular to the line, to the path, and that distance is 20 feet. Okay, 20 feet. Once again, I labeled the number there. You got to be careful when you put a number in your general picture. Am I allowed to put that number there? Yes, because this searchlight is not moving. It is rotating, okay, but the location of it is not changing. So it's always going to be 20 feet from the path. But the way I drew this picture, the searchlight would be, if you imagine the pen is the searchlight, it would be pointed in this direction because it's going to always be shining on the man. If the man moves to here, then it's going to rotate to there. Okay, so this is going to always be rotating. When the man gets to there, it'll be rotated to there, so it's shining on him. Okay, but it always rotates, but it never leaves that location. So I'm okay to label that 20 there. Okay, now what I'm going to do is I'm going to draw a triangle. I'm going to draw a line from the searchlight to the man. Let me go ahead and write down searchlight. You can draw one, but I'm probably going to draw a horrible searchlight, so I'm going to just label it a searchlight. Okay, now what other things do we need to label? Well, they tell you the man's speed is 4 feet per second. So remember, the derivative of position is speed or velocity. So I need to label the man's position. So what I'm going to do is I'm going to label the distance from here to here. I'm going to call that x. Now I know later on in the problem they say the man is 15 feet or something from this point, but right now this distance is changing. So the distance from here to here is changing. As the man moves to the right, that distance x gets bigger and bigger. So since it's changing, I'm labeling it with a letter. I'm not putting a number there. But this distance never changes. Also, because they talk about rotating, whenever you hear rotating, you want to think of an angle. So they're talking about this angle over here. Okay, because the searchlight is rotating, and as it rotates, it makes an angle between the direction it's pointing and then this direction here, and that angle keeps changing. So since it changes, I'm putting theta here. I'm not putting an actual number there. Okay, so there's the general picture. Now I'm going to draw another picture for at the specific instance when they're asking us to find something. So now I'm going to draw the same picture again, but basically I'm going to label the other quantities now that are given at that specific instance. So this is still 20. And let's say at the instant that they're asking us to find something, let's say the man is right here. He's still going 4 feet per second this way. Okay, so now I'm going to bring back the problem and let's keep reading it before we finish that picture. Okay, it says, at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? I know that a couple of sentences might be a little confusing, but let's see. It says, the man is 15 feet from the point on the path closest to the searchlight. This is the point that's on the path closest to the searchlight. They're saying the man is 15 feet from that, so they're saying this is 15. So now I'm going to label this as 15 feet. Understand the difference though. That distance is not it's changing. It's not always 15 feet. That's why I'm calling it x in my general picture. But then at the moment when this is 15 feet, we have to find something. Okay, I'm not going to label the theta because they don't give it. So that's pretty much, I guess I could just put theta in here again since we don't know it for now. Okay, so, but anyway, this is the general picture. This theta is changing with time, this x is changing with time, this is not. But then at the specific instance they're talking about, that's when this is 15. I don't really know what this is, otherwise I would put that there too. But when this is 15, find whatever they're asking for. Okay, so now we need an equation. So equation. So to get the equation, let's take a look at our original picture over here, the general picture. Use the general picture to get your equation. So I need some kind of equation that relates to x and the theta. If you were thinking Pythagorean theorem is not going to work because Pythagorean theorem will relate this side and this side, but we won't have theta in there at all. And they don't mention anything about this side at all. But we need to get theta in there. So think more along the lines of SOHCAHTOA. So which trig function would you use so that you can get sine, cosine, tangent of this angle, deal with x and 20? And I think it's tangent, because tangent is opposite over adjacent. That's opposite and that's adjacent. So the equation is going to be tangent theta equals opposite, which is x, over adjacent, which is 20. Okay, so in general, when you're doing a related rate problem, you draw the picture, general picture, and then write an equation down. After you have the equation, then you take the derivative of both sides. Now, I could take the derivative of both sides here. It's not a big deal, but I'm worried a little bit that some students are going to use quotient rule when you take the derivative of this. Don't use quotient rule when the top or bottom of your fraction is just a number, like we have this number on the bottom here. So don't use quotient rule. You can, but it's just a waste of time. Now, another thing you can do is you can just move the 20 over here. You can multiply both sides by 20. So I'm going to write down an equivalent equation and write down that 20 tangent theta equals x. So this will be the one that we'll focus on instead. It doesn't really matter though, you can use that one. I just like to put the 20 over there. So then what you do is you differentiate both sides. So now to differentiate both sides, let me get another paper out here. Actually, maybe I don't need another paper for this one. So differentiate. Okay, so 20 tangent theta equals x. So we're going to take the derivative of both sides with respect to time, because remember, time is the variable in this section. Okay, so when you take the derivative of this, when you have a number in the front, you copy it down. This is not tangent t. If that was a t, you take the regular old derivative because t is the variable. That's tangent of something else. So think of this as tangent stuff, and you're going to have to use a chain rule. The derivative of tangent stuff is secant squared of the stuff times the derivative of the stuff. What's the derivative of theta? d theta dt. And what's the derivative of x? That might be a little confusing because it's so easy. But the derivative of the letter is just the derivative of the letter. It's just the derivative of x. The way we'll write that is dx dt. Okay, now let's go and see what they were asking us to find. So I'm going to bring the problem out here again. At what rate is the searchlight rotating? Rotating has to do with theta, but they're talking about at what rate is it rotating. If they're talking about the rate, they're talking about the derivative. So they're asking you to find what quantity. If you said d theta dt, then you had it right. So they're asking you to find d theta dt. So what I'm going to do now is I'm going to take this equation and solve it for d theta dt. Let me do that here. So let me divide both sides by 20 secant squared theta. And that's going to give us, let's see, so we have d theta dt here. And you could just leave this like this if you want, but what I'm going to do is I'm going to go and move this to the side. So I'm going to take the dx dt, basically move it off to the side here, and you get 1 over 20 secant squared theta equals times dx dt. Okay. And one last thing we can do is we can write down, let's see here. Secant is 1 over cosine. So what's 1 over secant? The answer is cosine. But this is secant squared, so what's 1 over secant squared? Cosine squared. So instead of writing secant squared down here, I'm going to put cosine squared up here. We'll leave the 20 down here, and you get cosine squared theta over 20 dx dt. Okay, so that's going to help us. That's not the answer or anything, but we're getting there. Okay, so let me separate off this work that we did here, and I'll write this stuff on the next page. So after we differentiated both sides, we ended up with d theta dt equals cosine square theta over 20 times dx dt. Okay. So now that we have that, what do you want to do? Now you plug in the numbers. So now you plug in the numbers. Okay, but what numbers are we going to plug in? Well, let's go and look at our specific instance now. They want us to find d theta dt at a specific moment, at this moment. So at this moment, we know now that x is 15. Okay, you know, there's no x though. We're not going to be plugging in x anywhere. Well, let's see what numbers we do have. We do have dx dt. Remember what dx dt is? That's the speed of the guy. X is the position of the guy. The derivative of the position is the speed or the velocity, so that's dx dt right there. So we have dx dt is 4 feet per second. And then what about this theta? So now the only thing is we would have to find theta and plug it in. So you could find theta if you wanted to. Let's take a look at our specific instance again. If you wanted to find this theta, you totally could. You could do tangent of theta is 15 over 20. You could do tangent inverse and you can get what theta is. So you could find theta and then plug in the theta in there and be done. But I do want to show you a trick. It is not necessary to find theta. Take a look at the specific instance one more time. I know that I would like theta, but the truth is I don't really need theta. I need cosine theta. Let's look at this again. I need to know what cosine theta is. So if you knew the angle was 30 degrees, let's say, then you'd put cosine 30 degrees there. But if you don't know that theta is 30, but for some reason you knew cosine was 1/3, then you can put 1/3 there for cosine and be done with it. So here's what I'm asking you now. In this specific instance, what's cosine theta? So you can figure that out by, now I'm going to use Pythagorean theorem. I'm going to get this side here. Let's call this length L. And then we'd have L squared equals 20 squared plus 15 squared, which is 400 plus 225, which is 625. So L is the square root of 625, which is 25. Okay, so this side is 25. And then tell me what cosine theta is from this picture. Well, cosine is adjacent over hypotenuse, this over this. So I ran out of room to put it here. Cosine theta is, what do we say again? Adjacent over hypotenuse, 20 over 25. If you want to simplify that, you can simplify that to 4/5. So at the specific instance that they're asking us to find the derivative of theta, cosine theta is 4/5. So I know dx dt is 4/5. Dx dt is 4, and I know cosine theta is 4/5. And they wanted us to find d theta dt. Okay, So now we can go ahead and plug in the numbers, and here's what we get. So I'm plugging over here d theta dt. So cosine squared theta, but cosine is 4/5, so it's 4/5 squared over 20 times the x dt, which is 4. So what I'm going to do now is I'm going to take this 20 and move it by the 4, so it's 4 over 20. 4 over 20 simplifies to 1/5, and then I'll put this 4/5 squared over here on the side. So 4/5 squared times 1/5. If you multiply that out, you get 16 on top, and you get 125 on the bottom. Okay, so that's d theta dt. A couple of little things I want to mention, and then we'll be done. Let's get the units right. Well, what are the units? So to find the units, I need to know what are the units of theta and what are the units of t. Theta, what units do we use? I know angles are usually in degrees or in radians. Which one do you think we're going to use? The answer is always radians in this class. So radians, and then divided by, because it's like a divided by here. What's the units for time? In this problem, they said he was moving at 4 feet per second, so the unit for time is seconds, so it's radians per second.